Hello, fellow mathematician. This is Miss Backfish, and I am here to go over our dual enrollment lesson 4.3, which is right triangle trigonometry. And it basically gets into some things that we need to look at before we get into the unit circle, pretty much. So the first thing is, what do we mean by trigonometry? Well, trigonometry really means triangle measure. Trig is, tri, 3. Metry is measure, so triangle measure. But some of these you're familiar with, and some of them maybe not so much. You've already in geometry learned about sine, cosine, and tangent. And remember that sine is actually spelled with an E. We use the abbreviation so much that people forget why we say sine. They're like, why don't we just say sin? Well, just like we don't say cos, or sometimes we do say tan, but that's how you actually spell the word. Okay, the first thing I want to talk to you about is that there are 3 more trigonometric functions, and that they are reciprocals of these 3. So first off, let's define these 3. The sine of an angle is the ratio of the opposite side length, the side length that is opposite from the angle, over the hypotenuse length. All right, the cosine is the ratio of the adjacent side length, or the length of the adjacent side, over the hypotenuse, and the tangent is the ratio of the opposite side length over the adjacent length. Okay, so now there are 3 others, and they kind of go with these in terms of reciprocals. The first one is the cosecant. And I'm saying that it's first because it is the reciprocal of the sine. Reciprocal means flip it upside down, right? So instead of being the opposite over the hypotenuse, it's the hypotenuse over the opposite. Okay, then we have the secant, which is the reciprocal of the cosine. So instead of adjacent over hypotenuse, it's hypotenuse over adjacent. And finally, we have the cotangent, which is the reciprocal of the tangent. So instead of opposite over adjacent, it's the adjacent over the opposite. Now, there's another way sometimes we write this. But first, before I get into that, I just want to point out a very basic math fact that sometimes people have trouble getting. This means reciprocal. If I take something and I put it under a 1, that's basically going to flip it over. Let me give you an example. Let's say my x is 2/3. Then 1 over x means 1 divided by 2/3, or 1 divided by 2/3. And the way we divide a fraction is we multiply by the reciprocal. So 1 over x is 3/2. So this is just a fancy, or not even fancy, this is just a sort of shorthand way of saying the reciprocal. So if I say 1 over x, it doesn't necessarily mean you have to put it under 1. It means you have to flip it. So another way of saying this is I can say that the cosecant, which we sometimes abbreviate CSC, is the abbreviation, I can say this. Usually we go ahead and put an x or a theta or some sort of variable in there. The cosecant of my angle is 1 over the sine. It's just the same as saying it's the reciprocal of the sine. The secant of whatever angle is the reciprocal of the cosine. And the cotangent is the reciprocal of the tangent. So these are reciprocals of one another. All right? Sine goes with cosecant. Cosine goes with secant. I'm trying to make sure and tangent and cotangent go together. One way that I keep straight in my head, or at least I did when I was learning this, which of these goes with which of these, is that each pair has one that has co in it. Sine doesn't have co in it. The one that is its reciprocal does have a co. It's cosecant. Here we already have a co, so it's the one that's not co. And here the co over here. So each of these pairs of reciprocal functions has one that's a co. All right, so let's look at this with respect to a right triangle. Let's suppose I have a right triangle, and on my right triangle I have, let's say it's a hypotenuse of 17 units and a leg of 6 units. And I tell you that I want the values of all of the trigonometric functions for this triangle. All right, let's say I want them, I could do all of them for either, I could do all of them for both angles, but let's just pick one. Let's just say for this angle, for that particular angle of the triangle. All right. First thing I need to do is I need to find the missing side. How do we find the missing side if we have 2 out of 3 sides of a right triangle? Pythagorean theorem. So my leg squared plus the other leg squared equals the hypotenuse squared is Pythagorean theorem. So that means hypotenuse squared minus one of the legs squared will give me the other leg squared. So if I want the leg, I take the square root of that. And I had a feeling that wasn't going to simplify, so it's square root of 253. I deliberately wanted to use a messy number. And looks like I have succeeded spectacularly. Okay, so sine of theta. The opposite is the side that does not touch that angle, so to speak. Every angle is made of 2 sides. The 2 sides the angle is made of are the hypotenuse and one of the legs, because the only 2 angles we'll ever look at in a right triangle are one of the 2 acute angles. We never look at it from the standpoint of the right angle. So we'll either be looking at it from this standpoint or this standpoint, in which case one of my sides of my angle that I already have is the hypotenuse, and the other one we call the adjacent. So this would be my opposite. So let's go ahead and label those, since I'm not going to do it the other way as well. And my sine is opposite over hypotenuse. Great. That means my cosecant is the reciprocal of that. Now the cosine is adjacent over hypotenuse. So cosine here is going to be root 253 over 17. That's all very fine and well, but then when I flip that for the secant, I'm going to have to rationalize it. I can't leave a radical in the denominator, so I have to come through and multiply by that radical on top and on bottom. And my value would be 7 times root 253, 17 times root 253 all over 253. And then finally, we have our tangent of theta is going to be 6 over, here's another one we're going to have to rationalize, opposite over adjacent. And when we rationalize that, it's going to be this. And then my cotangent is going to be root 253 over 6. So there are my values of the 6 trigonometric functions with respect to that particular right triangle. The next thing we need to remember from geometry when we're working with right triangle trig is that we have certain special right triangles that come up in a variety of special scenarios, but are absolutely foundational to what we're going to do with right triangle trig in trigonometry or pre-calculus. They're foundational to the unit circle. So let's go back and review special right triangles real quick. There are 2 special right triangles that we study in geometry and in trigonometry. And one of them we generally call a 30-60-90 triangle, and the other one we generally call a 45-45-90 triangle. Now a 45-45-90, if we have 2 angles that are congruent, that means we have 2 sides that are congruent. So another name for this would be a right isosceles. It's every right triangle that is isosceles is a 45, 45, 90. Now in a 30, 60, 90, we have two legs and we have a hypotenuse, and the two legs are not the same length. One of them is smaller than the other. The smaller leg is the one that's going to be across from the smaller angle. So this is my smaller leg. Sometimes we call it the short leg. So I'm going to call that the short leg, which makes this the long leg. And this is my hypotenuse. And generally our rule, we start with the short leg. If I know the short leg, let's call that x, then the long leg is square root of 3 times x. Or sometimes we write that x times the square root of 3. Okay? The hypotenuse is related to the short leg 2 to 1. So this is 2x. These ratios are true. This is the ratio for every 30, 60, 90 triangle, because every 30, 60, 90 triangle would be similar to this one. So the ratio of the side lengths on similar triangles is going to be the same. Okay, so let's take, for instance, and you may encounter this in your homework. What if the short leg has a length of 1? Okay, if this is 1, then this is 1 times the square root of 3, or just square root of 3. And this is 1 times 2, or just 2. So that's a 30, 60, 90 triangle that you'll see pretty often. Keep in mind, anytime you have a right triangle where the hypotenuse is twice as big as one of the legs, it's automatically a 30, 60, 90. Now in a 45, 45, 90, we don't have a shorter or a longer leg. They're the same. We just said if these angles are the same, then these sides have to be the same. So we usually just refer to them as leg. Both of them are a leg, and then we've got a hypotenuse. And it doesn't matter which one of those you start with, they're the same. They're both x. The hypotenuse is the square root of 2 times x. Or you could write that as x root 2. Okay, so let's suppose that my leg is a length of 1. Then this one would be 1, and this one would just be square root of 2 times 1, or just square root of 2. Now in pre-calc or trig, we don't want to just work with degrees. We also want to talk about things in terms of radians now. So let's just think about using the conversion factor to change these to radians. Remember, our conversion factor is pi over 180, or 180 over pi, because 180 degrees is the same as pi radians. So if I'm trying to go from degrees to radians, I put the pi part on top, the part I want to end up in. So 30 times pi over 180. Basically, this just becomes a problem of simplifying. I can get rid of the zeros, like dividing by 10. 3 over 18 is the same as 1 over 6. So 30 degrees is the same as pi over 6. What about 60? 60 times pi over 180. 60 pi over 180. Get rid of the zeros, like I'm dividing by 10. And 6 over 18 is 1 over 3. So 60 degrees is pi over 3. Keep in mind, that's the same thing we got when we talked about looking at these angles of rotation. 30 degrees, 1/3 of 90. 30 degrees is pi over 6. And 60 degrees is 2/3 of the 90. So 60 degrees is the pi over 3. So we can actually apply this to that triangle, my 30, 60, 90. And we can say a 30, 60, 90 triangle is basically a pi over 6, pi over 3, 90, which is pi over 2, by the way, triangle. Now, let's take that a step farther, and I mean, you could just as easily use the 1, the square root of 3, and the 2, but yeah, let's do that. Okay, so if this is 1, if the short leg is 1, then the long leg is 1 times square root of 3. If the short leg is 1, then the hypotenuse is 2. Now, this is all based on whatever the short leg it is. So, you know, if this was 4, it would be 4 times square root of 3, and 8. So we can, since it's all proportional, and since it's all about ratios, and they're all similar triangles, we can just use one example like this, with the 1, the root 3, and 2, or we could have used the 4 root 3, and the 8, any of them, to find our trig values. In other words, if I want to know what the sine of pi over 6 is, Sine is opposite over hypotenuse. So opposite hypotenuse, it's 1/2. If I want to know what the cosine of pi over 6 is, adjacent over hypotenuse. What if I want to know what the secant of pi over 3 is? Well, remember the secant is the reciprocal of the cosine. Cosine is adjacent over hypotenuse, so what I want to do is hypotenuse over adjacent. So hypotenuse is 2, adjacent is 1, and that's the secant of pi over 3. And I could use this to find the values, the trig values for any of the 6 trigonometric functions for 30, 60, 45, or pi over 6, pi over 3, or what's 45 degrees? In radians, that would be 45 over 180 is 1 over 4. So it's pi over 4, as again, we saw here. Halfway from 0 to 90 is 45, that's pi over 4. So if we're asked about pi over 4, for instance, how about the cotangent of pi over 4? Cotangent of pi over 4, I could think of this as pi over 4. So cotangent, instead of opposite over adjacent for tangent, cotangent is the reciprocal, so it's adjacent over opposite. Really either way, same thing either way on this one. How about the cosecant? Let's do the cosecant of pi over 4. Knowing that pi over 4 is the same as 45 degrees, so I can use my 45, 45, 90. Cosecant is the reciprocal of the sine. So go to 45 degrees. Sine is opposite over hypotenuse. So I'm going to flip it over and do hypotenuse over opposite. Okay, so here I consolidated my little triangles of my 30, 60, 90 and my 45, 45, 90 with just a basic sampling of how the sides relate to each other, starting with the short leg being 1 here or either leg being 1 here. And the reason being is that I want to show you a couple of types of problems that you can do with this, or some basic calculations really is what it is. What if you're asked to do the tan of pi over 3 plus the sine of pi over 4? Tan of pi over 3. Here's pi over 3. Tan is opposite over adjacent. So opposite over adjacent is square root of 3 over 1. Plus sine of pi over 4. Sine is opposite over hypotenuse. So that's 1 over square root of 2. All right, now if I were giving that as a decimal, life would be kind of easier. If I'm going to give it in exact form, I do need to get a common denominator. I'm definitely going to go with 1 as my common denominator. And I can do that by multiplying. Actually, no, I'm not. I'm going to go with 2. Sorry. I can rationalize this guy. Make that root 2 over 2. And then multiply this by 2 and this by 2. And then what I have is 2 root 3 plus root 2 on top, all over 2. That does not simplify because 2 only divides out of this part, not this part. So that would be my final answer there. All right, what if I am doing cosine pi over 3 times the sine of pi over 4 plus the tan of pi over 6. Okay, cosine pi over 3. That's adjacent over hypotenuse. That's 1/2. Written next to each other like this means times. So sine pi over 4, opposite over hypotenuse. That's 1 over square root of 2. which really, if we're going to keep getting that again and again, we should just maybe use that in its rationalized form, square root of 2 over 2. So keep that in mind. So when I multiply that, and let's go ahead and think of it that way. This is square root of 2 over 2. When I multiply that, I get square root of 2 over 4. Tan of pi over 6. Here's pi over 6. Opposite over adjacent is 1 over root 3. Okay, it looks like to get a common denominator on this one, I'm just going to multiply by denominators. I think it's probably the easiest way. Multiply by root 3 on top and bottom there, and multiply by 4 on top and bottom here. And I get square root of 6 plus 4 all over 4 root 3. One last type of problem I wanted to show you, because I want to show you that it comes from this, or how we use this. It says, given that f of theta is equal to sine of theta minus 2 cosine 3 theta. Find f of pi over 3. Okay, so let's start by plugging in sine pi over 3 minus 2 times the cosine of 3 times pi over 3. Okay, 3 times pi over 3 I can simplify pretty quickly. 3 times pi over 3 is just pi. So minus 2 cosine pi. Okay, so sine of pi over 3. Opposite over hypotenuse. Square root of 3 over 2. Minus 2 times cosine of pi. Well, I didn't mean to give you one like this because we haven't actually done cosine of pi yet. That's silly. I'm sorry. I gave you a bad example. But that was really sad. I'm trying to think of how I could change this to make it a valid example. I think we're not going to try to do that. I think I'm just going to go ahead and tell you that the cosine of pi is -1. And you're going to see why in a later lesson. Okay? So then we would just simplify, and we could write it like this, or I could get a common denominator over here and have this, which we usually would put the radical part second, but it's not a big deal there. All right, sorry about this. We'll come back to that in another lesson. The last topic we need to talk about in this particular section is that of cofunctions. Now, this is not to be confused with reciprocal functions, which we talked about here, like that the cosecant is the reciprocal of the sine, the secant is the reciprocal of the cosine, and so on. Those are reciprocal function relationships. Cofunction relationships are a little different than that. Cofunctions are based on this concept. Let's say I have an angle theta, and I'm going to say this side is A, this side is B, this side is C, right? And let's say I have another angle. Let's call this angle, what do we want to call it? How about beta? We like to use Greek letters for angle names. It's a thing, okay? So what is the sine of theta? Sine of theta is opposite over hypotenuse, A over C. Okay, what's the sine of beta? Sine of beta, opposite over hypotenuse, that's B over C. What is the cosine of theta? Cosine of theta, adjacent over hypotenuse, B over C. What about the cosine of beta? Adjacent over hypotenuse, A over C. So we actually could put an equal sign right there. We can say that the sine of one of these two angles is the same as the cosine of the other one. Sine of one of the two angles is the same as the cosine of the other one. Okay, why is that? Well, whatever is opposite from this angle is adjacent to this angle. whatever's opposite from this angle is adjacent to this angle. So this is a relationship that's always going to hold true. Now, what relationship always holds true about these two angles? These two angles, my two acute angles of a right triangle, the two acute angles of a right triangle always add up to 90 degrees. They're always complementary because remember, all three angles would be 180. This is 90, already being used here. 180 minus 90 says that theta plus beta here has to be 90 degrees. Remember that the other way I can say 90 degrees is pi over 2. Okay? So another way of saying what we said down here is that the sine of one angle is equal to the cosine of that angle's complement, meaning 90 minus that angle. Or pi over 2 minus that angle. So the sine of an angle is equal to the cosine of its complement, meaning the angle that together with that adds up to 90 or pi over 2. That makes sine and cosine cofunctions. Okay, so let's just look at that. And the other ones that work like that too. The cosine, I didn't really want to write cosine first, so let me just change that real quick. The sine, it doesn't really matter which one, but the sine of an angle, let's say it's theta, is equal to the cosine of its complement. Or we can write that in radians, and it works both ways. I could say the cosine of an angle is equal to the sine of its complement in radians or degrees. So sine and cosine are cofunctions. Notice it's the one same happens here. Secant and cosecant are cofunctions. If I have the cosecant of one angle, then that's the secant of that angle's complement. Or if I have the secant of an angle, that's the cosecant of that angle's complement. And I'm trying to use pi over 2 and 90 interchangeably. It does not matter which one it is because those two mean the same thing. So secant and cosecant are cofunctions. Guess what else is cofunctions? I bet you can guess. Last ones. Tan and cotan are cofunctions. Whatever the tan of some angle is the same as the cotangent of that angle's complement, which means 90 minus that angle or pi over 2 minus that angle. The cotangent of an angle is the tangent of its complement. Pi over 2 times minus that angle or 90 minus that angle. Anytime you see 90 here, pi over 2 could also substitute there. Anytime you see pi over 2, 90 could substitute. Same idea. 90 equals pi over 2. Those are cofunctions. So last but not least, we're going to go ahead and use cofunctions to complete some statements here. The secant of what is equal to the cosecant of 90 minus x? Secant and cosecant are cofunctions. So if we're talking about the cosecant of 90 minus x, that's the secant of x. Because x and 90 minus x are complements. The sine of pi over 6 is the cosine of what? Well, since we're saying pi over 6, this must mean in radians. So I could say 90 minus pi over 6 or pi over 2 minus pi over 6. Those are complements. And last but not least, If theta is an acute angle and the cosecant of theta is 4/3, then find the secant of pi over 2 minus theta. First off, I have to recognize that cosecant and secant are cofunctions. So whatever the cosecant of theta is, it's the secant of 90 minus theta. 90 minus theta is the exact same thing as pi over 2 minus theta. When you have a problem like this, they'll tell you exact form answer, no calculator. That's because you don't need a calculator. The cosecant of theta is the secant of pi over 2 minus theta. So if it's 4/3, it's 4/3. That's all it is. Hope this has all helped. And we will go on next with our further study of trig in section 4.2 after this one. Thanks for watching.